We welcome you to our second video on robot controllers, which builds on the basis from the overview of robot controllers video. It covers the core knowledge of robot controller design. In the last video, we looked at the fundamentals of robot control and received an overview in which typical robot control structures were presented. The PD control was also introduced, which we will take a closer look at in this video. We will focus on the physical meaning of the control parameters and how to select them. We will learn about the concept of the kinematic controller and we will see where the limits of the control parameters are. Let's go to know the control parameters of the PD controller. What are the suitable controller settings? The theory and explanations presented here are also suitable for people who did not have an introduction to control engineering. In particular, mechanical engineers can better understand the robot controls through these explanations. Let's look at the mechanical model of a proportional differential controller that is used to position a mass to a specific location. Let us assume that we want to move a mass to a certain position and apply a force to the mass for this purpose. A pointer of the mass points to the actual position. The target position is labeled with XD. We assume that the target position is connected to one plate and that the mass or actual position is connected to another plate. We connect the two plates with a spring constant Kp. In parallel, we also attach a damper. The damping constant is Kd. We refer to the position error between XD and X as position error E and the velocity error between xd dot and x dot as velocity error E dot. The spring force is proportional to position error and is then Fp equal Kp multiplied by E. The damping force is proportional to the velocity error and is Fd equal Kd multiplied by E dot. Putting this together gives the formula F equal Kp multiplied by E plus Kd multiplied by E dot, and we immediately see that this corresponds exactly to the PD controller. As a program example, it would look like this. You can see that Kp of the PD control corresponds to the spring constant and Kd to the damping constant. At this point, you can see that when formulating the controller, the actuator and sensor values should be expressed in SI base units, because otherwise you cannot understand position error, velocity error, Kp and Kd values, and because you lose the relation to physical reality. In the swung out state of equilibrium, the system is at rest. The position error E and thus the spring force is zero. The velocity error E dot and thus the damping force is also zero. The system is force-free. If the system is preloaded, the target position is displaced and the spring is under tension. The control error E is then target position xd minus actual position x and the velocity error is zero. The force F would then be a short moment Kp times E. Due to the force, the system makes a movement. If Kd, the damping constant, is zero, the mass oscillates sinusoidally around the set point value. If the damping constant is greater than zero, the mass oscillates but is viscously damped and reaches the set point after several oscillations. When the damping constant is equal to the critical damping, the mass reaches the set point without overshoot. The question now arises, how must Kp and Kd be chosen so that the actual value optimally follows the set point? If we look more closely at the forces, we see that the force of the spring Kp times E and the force of the damper Kd times E dot act on the mass and together gives the resultant force F. This resulting force leads to an acceleration which fulfills Newton's laws. The force is therefore mass times acceleration. This system can now be represented as a controller flowchart, which we already got to know in the video Robot Control Overview in the chapter about PD controllers. Newton's equation can be combined with the equation of forces to form a differential equation. To be able to solve the differential equation, we write it out so that the state variable x becomes visible. If you know the theory of the vibration equation, you can continue directly with the derived equations. For the others, I will briefly show the homogeneous solution of the differential equation. Let us consider the differential equation from before. Since we are interested in the homogeneous solution, we set xd to 0. This leads to the following homogeneous differential equation of second order, which looks familiar. We substitute the quotient kd by m with 2 delta and the quotient p by m with omega squared and obtain the well-known oscillation equation. I assume that x equals e to the power of lambda t, and I derive twice in order to get x dot and x dot dot. After inserting the substitutions into the vibration equation, I can shorten by e to the power of lambda t and thus get rid of my approach. I solve the resulting quadratic equation and get 2 solutions. If delta is greater than omega, I get 2 real solutions, which I combine with 2 freely selectable integration constants to 1 solution. The solutions are 2 overlapping decaying exponential functions. If delta and omega are equal, I get the solution for the critical case. However, this is only academically interesting because it hardly ever happens in reality that delta and omega are exactly equal. On the other hand, it is interesting when delta is smaller than omega. In this case, I get 2 complex solutions, which I again combine with 2 integration constants. In the next step, I break it out the decayed e function. However, x1 and x2 must be complex to represent the real x with this equation. This is not very elegant, so I transform the equation again with the Euler formula, and now I can insert 2 real constants, x3 and x4. Since I don't find the formulation with sine and cosine very practical, I reformulate again and now see a damping vibration equation with the start amplitude x0 and the start phase phi 0, with the natural frequency omega 0, the damping delta, and the damped natural frequency of omega d. Please note that the index 0 at the amplitude and the phase represent the initial value at the time 0, while at omega it indicates that it is the frequency of the undamped oscillation. The damping constant delta is often difficult to understand and interpret. I therefore put it in a relation to the natural frequency, which is done with Lair's damping ratio and is very illustrative. If we insert this into the known equations, we see that for a d smaller than 1, the root value becomes negative. The critical damping is therefore 1. If d is smaller than 1, we have damped oscillation. At the beginning of this derivation, we ask ourselves how we would have to set the controller constants to achieve a desired control response for our controlled system. We have now found this. Now we can specify the control bandwidth and damping as desired. The control stiffness, Kp, is then equal to omega squared times mass, and Kd is equal to 2 times d times omega times mass. With critical damping, the mass no longer overshoots in the case of a step response, but the follow-up behavior is slow. Therefore, it is better to choose a d of approximately 0.7 or 1 divided by the square root of 2, because in this case the follow-up response is fast and the overshoot is within an acceptable range. One can use the equation for translation, rotation, or in robot coordinates. Of course, one must use the variables and constants consistently linear or rotational. In the most general case, one forms a vector equation with generalized robot coordinates. In our example, we use translational representation. With these findings, our generalized PD-controlled system looks like this. We can determine and insert the parameters directly from the specifications. For better visualization, we can insert the meaning of the control parameters directly into the control diagram.